So this Friday is exam 1. And for exam 1, you're responsible for everything up through uniaxial tension and compression. So that means everything that we've done in class up until, like, the stuff from today is not going to be on the exam, but everything we did up through Friday is going to be on it. Let's look at the practice problems for a sec. Okay, so for the practice problems, so you should be comfortable with all the stuff up through 14. Yeah. Oh, with these things? So yeah, this stuff is just about understanding what the stress tensor, the stress element looks like. So yeah, you're responsible for all of that. We talked about that, and then I talked about, after this, we talked about the constitutive relationship, and then how to let's see. So yeah, if you just go through the notes in the order that we went through them, we talked about how to do all of these, and then you should know how to do these just simple trusses and how to get the states of stress and strain at points in the simple trusses. Okay.
You don't care how we solve those?
Nope, I don't care how you solve it. And there is an easier way to solve it than the way we did it in statics. And I'd be happy to talk to you about that, but I don't think I'm going to go over it in class because you're probably better off not learning a new method 2 days before the exam or whatever, but I'd be happy to talk to anyone about that.
1 through 14, right?
1 through 14, yeah. And then remember that there's a lecture quiz too, so you need to be familiar with your notes. All right, so, well, I guess first, anybody have any questions about practice problems or anything like that? I'd be happy to, anything related to the exam, I'd be happy to answer as many questions as anyone has.
On the changing angle one, on the strain.
Yeah.
Are you going to give the change, or is that going to give it 2 degrees?
Oh, I guess I remember somebody mentioning that. So that's, if it says 2 degrees, that really should be the change. Like, it should be, yeah, that's very badly drawn if that's 2 degrees. So I guess that would be 88 degrees. Yeah, right. Yeah, that's right. That's right. Any other questions? Yeah. Mm-hmm. Mm-hmm. In writing in the compliance matrix? Oh, I suppose you should write them in if I ask for the matrix, but I think more likely I'll just ask for the stress tensor and then ask for the strain,
But the answer is the same. It's when I plug in the dot values, I get the same answer.
Yeah, right. And you might want to program in that compliance matrix into your calculator before the test. It'll save you some time. especially if you have a TI calculator, that program is on D2L, like, so you can just enter it in like line for line and it should work. If you need help programming any of those in, you know, come to office hours, I'd be happy to help you program it. But otherwise, you're just going to have to enter 36 values every time. You know, it's a lot easier if you have the program. Any other questions? Okay, so we talked about let's say we can calculate the stress for cases like this and cases like this, where it's in compression. And once we can calculate, and the stress is uniform all the way along this, except that we don't know what's happening near the end here and near the end here. But everywhere else, the stress is uniform. But here is something that we can't calculate yet. So imagine that you have, so what about a fixed joint to the wall, let's say 1,000 newtons of force here at a 45-degree angle. Say this is 1 meter long. If you draw the free body diagram of the whole member, the fixed joint at the wall means that you have an unknown force vector, R, and an unknown couple, MR. And then over here, I mean, I guess I'll write this in components. That's negative 707.1, negative 707.1. Okay, so there's the free body diagram. So you don't, in this case, you don't have just axial loads. You have off-axis force vectors and you have a couple, and we don't know how to deal with that yet. So the way to deal with that is, or let me say, to calculate the stresses and what's this thing called, by the way? What's this object called? It is called a cantilever. That's not the one I was looking for, though. Beam. This is called a beam because now you have loads that are happening perpendicular to the long axis in addition to parallel. Okay. Okay, so to calculate stresses, you need to first calculate internal loads. And I'm just going to go through all this again. It's going to be very similar to how I did it in statics. But I don't know, it's good for you. Repetition is good for you sometimes. So let's start by, okay, so as an introduction to internal loads, let's say we're trying to figure out what are the internal loads at the dotted line. Okay, so I'm going to take the same object and I guess let's ignore the weight for now. And let's say that halfway out along the length, we're going to try to figure out what the internal loads are. Okay. So if you call this piece 1 and this piece 2, I'm going to do 2 calculations. So the first calculation is I'm going to figure out the loads applied to piece 1 by piece 2. And then second, I'm going to calculate the loads applied to piece 2 by piece 1. So I know this was last semester and you had a lot of other stuff going on as we did this. So where am I going with this? Anyone remember last semester well enough to, where's this argument going? So, okay, so eventually we're going to go to the cuts, and the first cut I'm going to make is along this dotted line. Where am I going with this by saying I'm going to first calculate the loads on member 1 by member 2, and then I'm going to switch to the other one? What's the point of doing that? Well, that's close. That's on the right track, but in fact, I'm going to show that they're not the same, and that's why we're going to need to use this in the lecture quiz. I called it the funny sign convention. Remember, so we're not going to end up using the like coordinate axes directions as our default positives like we're used to using. We're going to end up using this funny sign convention because we want these answers to match each other going both directions. Okay, so let's do it and you'll see what happens. So free body diagram of, well, first I have to figure out what the reaction loads are at the wall here. So this is a fixed joint, so we have the force vector R, we have the couple MR, and then we have the force vector over here, minus 707.1, minus 707.1. And you could write out the pancake artist table for this, but these tend to not be too complicated to do, so I tend not to do those, write out the full table, but I'm going to choose my about point here at the left end. Newton's second law, add up the force vectors and you get Rx, Ry. Well, let me do, should I do that table once? Would that help? Okay, I'm going to do it. All right, so the first load I'm going to look at is this force vector R. If we put the coordinate system here, then the location where that force is applied is 0, 0. The about point, I'm going to always put that at the left end of the beam, so that's also 0, 0. So the row vector is zeros, the force vector is those two unknown components of R, and the cross product is 0. Now we have to deal with the couple MR. We don't need any of this for a couple, and the moment is MR. And then the last one is this force on the right end. The location there, the coordinates are 1, 0. The about point is still the origin. So the row vector is 1, 0. The force vector is negative 707.1, negative 707.1. And so the cross product is just minus 707.1. So Newton's second law says Rx, Ry plus negative 707, negative 707 is equal to zeros. And the rotational equation says Mr minus 707 is equal to 0. So solve that for the unknowns, and that force vector on the left is equal to positive 707, positive 707, and the couple at the left is positive 707, and that's Newton meters. Okay. So now we know all of the external forces on this, and now we can isolate, where did I put it? Now we can isolate piece 1 to calculate the loads on piece 1 by piece 2. Okay. So free body diagram of piece 1. Has the external loads on it that we just calculated. What other loads are acting on this piece? Yeah, I'm not going to do it that way yet, but you're right. But the way I'm going to do it is I'm just going to think of this as, so the stuff happening over here, we're not isolating that. So this force doesn't apply. But what does apply is there's a fixed joint between this member and this member. It's like these two are welded together, right? And so that means that there is an internal force vector, F, and there's a couple. I'll call this Fi for internal force, and I'll call this Mi for internal couple. And the reason we have these loads is because it's a fixed joint with the adjacent material. We could write out the table again for this, but again, I'm going to have the about point here, and because the geometry of this is pretty simple, I'm just going to do these calculations in my head. So Newton's second law says add up all the forces, they have to be equal to 0. So 707.1, 707.1 plus Fi, X and Y components, is equal to zeros. So that internal force vector, or another way to think of it is the force on 1 by 2, is equal to negative 707.1, negative 707.1. And the rotational equation, and I'm calculating these moments about the left endpoint. So add up all the moments, those have to be equal to 0. So we have positive 707.1. And this force Fi, what moments does that produce about the left end? Yeah, only the Y component produces a force. And you could think of, well, I'll just write it first as If Fiy was positive, it would produce a counterclockwise rotation, right? So that's a positive moment because it's counterclockwise. And so that means that we have the moment arm of 0.5 times Fiy, and then plus Mi is equal to 0. So I can rewrite this since we know what Fiy is. So minus 353.5 plus Mi is equal to 0. And so Mi, which you can think of as the couple on 1 by 2, is equal to minus 353.5 Newton meters.
So you're trying to prove that F21 is negative F12.
Right. Yep. And if you think of it in terms of Newton's third law, it also has to be the case, right? I mean, you know that if we just switch these subscripts, the force on 2 by 1 has to be equal to the negative force on 1 by 2. But instead, I want to do this by doing the problem again, by isolating, remember, piece 2, calculate those forces, and we're going to see that they're equal and opposite, okay? So now, part B, isolate piece 2. So now there's all this part of the member that isn't included in our free body. We have this external force of negative 707, negative 707. And over here, we have the force vector F, I guess I'll call this Fi again. And I'll call this Mi. So Newton's second law says Fi, x and y components, plus negative 707, negative 707 is equal to zeros. And so Fi, which is equal to the force on 2 by 1, is equal to positive 707, positive 707. And that's equal to negative F12. That had to be true from Newton's third law. And then the rotational equation, I'm going to calculate the moments about the right endpoint. So what moment is produced by this 707 force, the force at the right? Well, since I'm doing the moment, since my about point is this one doesn't do anything, okay? Doesn't produce any moment. Sure. So rotational Newton's second law says that there is a clockwise moment of 0.5 times Fiy. And then add in mi, that's equal to 0. We know what FIY is, so that's 0.5 times positive 707.1 plus mi is equal to 0. And so mi is equal to negative 353.5 Newton meters. And that's equal to negative, and let me write this as, so this is equal to the couple on 2 by 1. And that is also the opposite of the couple on 1 by 2. This is also required from Newton's third law. Can anyone think of an argument why Newton's third law has to work for couples the same way that it works for forces? Because, yeah, that's exactly right. So if you think of a couple as just like a moment that's applied, it isn't obvious. But if you think of a couple as being two equal and opposite forces, then each one of those forces is applied, in this case, on member 2 by member 1. And Newton's third law has to work for those forces, so it has to work for the couple too. Okay. And so the point, so why did I do all this? The point is, what are the internal loads Fi and Mi? You get different answers depending on which side you work from. Maybe this wasn't so clear in triple speed. Depending on which side, left or right, you work from. The answer or the solution to this problem, because it is a problem, we want there to be a specific internal load that we calculate no matter how we calculate it. So the solution to this problem is to choose a sign convention that gives the same answers from either side. So our sign convention is going to be this. If you're working from the left, and over here, if you're working from the right, if you're working from the left, the horizontal component of the of that internal force that's applied by the fixed joint between the two parts is going to be represented as pointing out of the cut toward the right. And if you're working from the right, that same value t is going to be represented pointing to the left out of the cut. The vertical component of that internal force is going to, if you're working from the left, you're going to treat it as positive if it's going down. And if you're working from the right, positive means that it's going up. And the moment that, and again, that moment has to be applied because it's a fixed joint between the two parts. If you're working from the left, it points that way. And if you're working from the right, it points that way. Okay. You can think of these as equal and opposite loads acting on an infinitesimal sliver of material, infinitesimal of material acting at the cut. So right at the cut, we're going to assume that you have this sliver. It's really infinitesimal. I drew it with some thickness there, but just so you can see what so there's tension this way, tension this way, okay? And then for V, there's a shear force that way and a shear force that way. Whoops. B. And then for the bending moment, they're like this. And it's easy to remember the sign convention for the moment because the bending moment sign convention is positive if it does this to the sliver, you know? Yeah, and it's negative if it does this. The other ones, though, you're on your own. There's no easy way to remember the other ones. What? Yeah, I guess. I don't know. Okay, so M is called the bending moment. V is called the shear force. And T is called the tension. And notice that the shear force, so if you have something subjected to shear force, that has the effect of deforming it in a shear deformation. Okay, so there's a relationship between these shear forces and a shear, like a change in angles of this material. If you push down on one side and up on the other side, the effect is to change the angles. Okay. All right, so because I know you kids love to see the same problem over and over again in different ways, I'm going to do this problem again, but with the sign convention. Okay. Okay, so here's the problem again. Negative 707, negative 707. And if we solve it, let's just go right to the isolated body. So we know that we have a force of positive 707, positive 707, and a couple of positive 707. So I'm going to isolate piece 1. This is working from the left. So we have this external force, 707, 707, and we have that external couple of 707. And now the loads coming from this fixed joint between this piece and the piece next to it, instead of using the sign convention for couples and vectors, now we're going to represent it as this force T in that direction, force V in that direction, and a force couple M. Newton's second law says add up all the forces. So 707, 707 plus, now you have to be careful with, so we have this funny sign convention that doesn't correspond to the vector sign convention, right? And so now you have to be careful with the signs when you express these as vectors for Newton's laws. So the tension, is that pointing in the positive x direction or negative x direction? Positive. So this tension force vector is represented like this. And the shear force, is that in the positive or negative y direction? Yep. Yes, yep, that's fine. I usually do that too. And so from this, you get that T is equal to negative 707. V is equal to positive 707. And now the rotational equation with the about point at the left says the couple at the left plus M. Remember, this distance is 1/2. So we have a clockwise couple about the left point produced by the moment arm of 1/2 times V. So negative 0.5 V is equal to 0. And if you solve that, plug this in for V, you get that M is equal to negative 353.5 Newton meters. Yeah.
Why the negative 0.5? Okay.
That makes sense? Okay. So All right, so these are our answers working from the left. You're like, no, don't do it. Don't do it. We believe you. No, I'm doing it. So I'm going to work from the right now. And what should we see for these values? Yep, this time we're going to see that T is going to come out to be negative 707, V is going to be positive 707, M is going to be positive, that should be negative, shouldn't it? But anyway, it should match. M is going to be negative 353 again. Okay, so we have this force vector of negative 707, negative 707. And then we have the internal loads. And remember to use the right directions for working from the right. So we have T here, bending moment M, and the shear force V. Newton's second law says, so with that T, is that in the positive or negative x direction? That's in the negative x direction. So this is negative T0. Is the V in the positive or negative y direction? Yep, so this is 0 positive V. And then add on this external force. So T is equal to positive 707, V, negative, yeah, thanks. V is equal to positive 707. So those match with what we got going the other direction. And then the rotational equation with the about point on the right end. There's no moment produced by this. There is a clockwise moment produced by that couple M, so that's negative M. There's a clockwise couple produced by the moment arm of 0.5 times V. The tension doesn't produce any moment. And so we get that negative M plus 353.5 is equal to 0. And so M is equal to positive 353.5. Wait a second. Minus, oh yeah, that's clockwise, right? Thank you. Okay, so this, since our about point is here, a positive value of V would cause a clockwise rotation about this about point. And so this should appear here as minus 0.5 V. And so this is minus. And so M is negative 353.5. What?
Wasn't for the left side also negative? Shouldn't they be opposite?
No, in this case, they should be the same. Yeah, so that's the whole reason to use this new non-vector sign convention, is that now they match, and now we don't have to, if we were going to use that vector sign convention, we'd have to specify the internal load is this, and I work from the left. We don't want that. We just want values for the internal loads. And so that's what this new sign convention gives us.
Do we get the same thing when you use M12 and M21? Do we also get same answers?
No, those were opposite. So those were using the vector. You did?
So I got one negative, one positive.
Okay, I probably did the same thing I did here. Yeah, let me just look. That won't take long. So working from the left, we got a positive value. We got that internal couple is negative 353. Working from the right.
I had it on the, when we did it before the first time, before we did the sign convention.
Mm-hmm.
I had both of those written as negative, and I don't know
from the right, we should have gotten, so this FIY produces a clockwise rotation, so this should be negative. And so, yeah, you should have gotten what you got, a positive value here. So the bottom line is, if you're using just the standard vector sign convention, all your answers are opposite. And then you have to specify which way you're working. We don't want to do that, so we have this new way of defining directions, positive directions, that lets us just say these are the values of the internal loads. Okay. And that was a question I asked on the lecture quizzes, and most people in the class got it wrong. And so I asked that same question again on another lecture quiz, and most people got it wrong again. So this time, you're going to get that one right. So what's the point of doing those, using this sign convention, the T, V, and M sign convention? The point is, it doesn't matter which direction you work from, you get the same values for those internal loads. Okay. So this is the idea of internal loads. The only thing that we have to add to it now is we have to be able to calculate the internal loads for every value of X along the length of the beam, not just at, all of these problems I just did for a single value of X. I just did it halfway through the beam. That's not enough. So we're going to have to come up with functions of X to tell us what these internal load values are as you go from one end of the beam to the other one. So that's what we'll do next time. Okay, that's it.